Today we are going to discuss the next chapter, inference for distributions. In this chapter, we are going to use 3 units to discuss 2 major topics. The first one is inference for the mean of a population. We are going to discuss T distributions, the one sample T confidence interval, the one sample T test, and the matched pair T procedures. The second topic is comparing 2 means. We are going to discuss 2 sample Z statistic, 2 sample T procedures, 2 sample T significant test, and 2 sample T confidence interval. Let's begin with an example. So sweetening colas. Cola manufacturers wants to test how much the sweetness of a new cola drink is affected by storage. The sweetness loss due to storage was evaluated by 10 professional testers by comparing the sweetness before and after storage. We have listed the 10 testers by 1, 2, 3, 4, all the way to 10. And the first one claimed that the sweetness loss is 2. Maybe 2, I don't know the unit, maybe 2% or 2 something. But anyway, that is not important. Right? So the first one says the sweetness loss is 2. The second one said the loss is 0.4. And the next one is 0.7. And the next one is 2.0. And the fifth says the sweetness actually increased. It is so the loss is negative 0.4, and so on. Right? Obviously, we want to test if the storage results in a loss of sweetness. Thus, the hypotheses are H0 is mu equal to 0. That means the mean of the loss, sweetness loss equals 0. That means no change. And versus the alternative hypothesis is mu is greater than 0. That means the average loss is greater than 0. That means there is an effect. This looks familiar, right? And we try to use the method we discussed in last chapter to solve this one. And we are given this sample, assuming it is a random sample, with a size of 10. Then what we do is the first one we calculate the z-score. So z-score equals x bar minus mu, then divided by the standard deviation. X bar is the mean of this random sample, so that's easy to calculate. We can just add all these 10 numbers, then divided by 10. And mu is the mean of the population that we want to test. Right? So in here, because H0 is mu equal to 0, so that's mu equals 0 here. Right? And now we have a question, because we don't know the sigma, which is the standard deviation for the population. Here, we know the population is the whole cola drink, but we only know the sample here. Right? We do not know the population parameter, the standard deviation sigma. Right? Maybe there are several reasons. The first reason is maybe the population of all cola drinks is too large, so we cannot do that. Second one is because this is a new cola recipe, so we have no population data. So anyway, we don't have this one. So this one we don't know. Now we stuck here because we cannot calculate the z-score, so we cannot calculate no matter the confidence interval or the significant test. And actually this problem is very common in real data. So we need to figure out a way how to process, how to deal with this kind of problem. When sigma is unknown, it means the population, when the population standard deviation is not known, and we are going to, our method is we are going to use the sample standard deviation as the sample standard deviation as use this to estimate the population standard deviation sigma. Because although we don't know the population, but we do know the sample. So we can calculate the sample mean, and we can calculate the sample standard deviation. And we call this sample standard deviation as S, and we are going to use this S to approximate sigma. Right? When how good is this? This estimation. When the sample size is large, the sample is likely to contain elements representative of the whole population. In that case, the standard deviation of the sample S is a good estimate of the standard deviation of the population sigma. But when the sample size is small, so when the sample size is large, that is good. But when the size is small, the sample contains only a few individuals, then S is not good estimate of sigma. But we can only, anyway, we can still use this. This is the only way we can to approximate the standard deviation of the population. Okay, now we have a way to deal with this. We said we are going to use the standard deviation of the sample to estimate the standard deviation of the population. Then, for a sample size of size n, the sample standard deviation S is calculated by this. We already know this from chapter 1. The standard deviation is, first I need to calculate the mean of the sample. Then, with each number minus the mean is the difference. Then take the square, then sum of all the squares, then divided by n minus 1. Right? That gives us the variance. If we take the square root of the variance, then this gives us the standard deviation. And here, n minus 1 is called the degree of freedom. When we discussed in last chapter, we know we have a sigma over square root of n. Now we don't have a sigma. Instead, we have S. So we have S here. Then S divided by square root of n is called the standard error of the mean. Scientists often present sample result as the mean plus the standard error of the mean. We have an example here. A study examined the effect of a new medication on the seated systolic blood pressure. The result presented as the mean plus and minus the standard error of the mean. For the 25 patient, so 25, this is n, so n equals 25, or 113.5 plus minus 8.5, 8.9. We know this one is the mean. So x the mean plus minus this. So this is called the standard error of the mean. And the result will be represented in this format. So that means this 113.5 is the mean of the sample of size 25. And 8.9 is the standard mean of the standard error of the mean, which is S divided by square root of n. What we are looking for here is what is the standard deviation S of the sample data. Although we are given this sample, but we are not directly given the standard deviation of the sample data. Instead, we are given in this form. So from this value, 8.9, we can calculate the standard deviation of the sample data. Because standard error of the mean equals S divided by square root of n. So SEM equals S over square root of n. And this is given as 8.9. And this one is what we are looking for. N is 25. So S will be equals SEM times square root of n. So 8.9 times square root of 25, which is 5. So 8.9 times 5 equals 44.5. And this is the S. So S equals 44.5. If you are working in any experimental field, if you are given the result as this format, so it is the mean plus and minus the standard error of the mean, then from this number, we know the standard deviation of the sample data. And we also definitely also know the mean of the sample. Okay, here we discuss a new distribution. It's called the T distribution. This is very similar to a normal distribution. Suppose a simple random sample of size n is drawn from a population who satisfy a normal distribution, whose mean is mu and the standard deviation is sigma. If the sigma is known, then from previous discussions we know the sample distribution satisfies also a normal distribution with the same mean, and the standard deviation is reduced by a factor of square root of n. This is the sampling distribution. This is the major topic of last chapter. But when sigma is not known, we are going to use estimation from the standard deviation of the sample S. In this situation, the sampling distribution is no longer a normal distribution. Instead, it will satisfy a T distribution. And that T distribution has a mean of mu and has a standard deviation of S over square root of n. So you can see these two are very similar. If we know sigma, then we just use sigma. If we don't know the population standard deviation sigma, then we are going to approximate it with the sample standard deviation S. Right? Then instead we do not write n, instead we write t. So that's called T distribution. Here we have an extra parameter. It's called degree of freedom. Because of n, so we have n minus 1. So that is df, degree of freedom, n minus 1. This n minus 1 degree of freedom is also very important. Once we know the T distribution, we can calculate one sample T statistic, which is T equals x bar minus mu, then divided by S over square root of n. If we compare in z statistic, z equals x bar minus mu, then divided by sigma over square root of n. So you can see these two actually are very similar. The only difference is here we know sigma, so we use sigma. If we don't know the sigma, then we are going to use S. And if we use sigma normal distribution, then we says this is Z statistic. Otherwise, we said this is T statistic. Hopefully, everybody already understands very well of the normal distribution and the Z statistic. So up to this point, we don't have any problem understanding the T statistic. So we should know the difference between this. Repeat. If we know sigma, then that is the Z statistic. And if we don't know sigma, we are going to use S instead. Then that gives us a T statistic corresponding to a degree of freedom n minus 1. So later time we are going to see the effect of n minus 1. Here, when n is very large, S is a very good estimate of sigma. We already know that. The larger the better. And the corresponding T distributions are very close to a normal distribution. That is also very reasonable generalization. The T distributions become wider for smaller sample sizes, reflecting the lack of precision in estimating sigma from S. So if we look at these several distributions, and this dotted line here Dotted line here is very wide, and here it is very little. Okay, so you can see wide. So if we use this one to approximate the population parameter, right, then we know we are going to, the precision will be less. So we are going to have a large error. So in this case, we are going to have a lack of precision. Right? So this means the sample size is small. So in this example, for this, the t degree of freedom equals only 2. Right? The degree of freedom df equals 2. That means n equals 3. Because df equals n minus 1. So means this sample has only 3 individuals. If we increase the size of the sample, for example, the second one here in the middle, this one is narrower than df equals 2. Actually, this one, the second one here is df equals 9. That means n equals 10. Right? There are 10 individuals in the sample. So this one here is narrower than the df equals 2, so that is a better approximation of the population parameters. Because the standard deviation is small. Definitely, if n is very, very, very large, so approaches infinity. Actually, if it's more from a later time, we are going to see if more than 100 or something, that is good enough. So it will something like converge to a standard normal distribution, which is represented by the most inside for this one, by this one. So this is a normal distribution corresponding to a t distribution with df equals very large. We assume equals infinity. So you can see this one is much narrower. That means the variation is smaller. So if we use this one to approximate the population parameters, it will give us more precision. This finishes the discussion of the difference between normal distribution and the t distribution, or the z statistic and the t statistic. They are very similar. Right? So now we are going to calculate some problems with the t distribution. As we know, this normal distribution and t distribution are very similar, so we follow almost the similar procedures. As with the normal distribution, the first step is to standardize the data. Then we use table D. For normal distribution, we use table A, but for t distribution, we use table D to obtain the area and the curve. So it's very similar. Look at it here. Before we said z equals x bar minus mu over sigma over standard deviation. So now we use t equals x bar, the mean of the sample, minus mu, then divided by s divided by square root of n. Keep in mind, we are going to have another parameter. It's called the degree of freedom, so n minus 1. When we look up table D, we need to use the df. After this standardization, we are going to convert any t distribution into a normal, standardized t distribution. So here, mu is the mean or the center of the sampling distribution, and the standard error of the mean at EM is standard deviation, the width. What we do is we obtain S first. Usually we are given the sample, then we need to calculate the standard deviation S by ourselves. In Z, in normal distribution or this statistic, usually this sigma is given because the population is very large. It's not easy for us to calculate the standard deviation. So most probably it will be given. But for sample, most of the time we are going to calculate this with the formula we discussed in first chapter, or from the formula we just discussed here, the standard error of standard error of mean equals S over square root of n. So we have two methods to calculate this one. The first one is S equals square root of n minus 1 here, xi minus x bar squared, then sum for all this one. So this is the first method. The second method is we use this standard error of the mean equals S over square root of n. If we know the standard error of the mean and if we know the size of the sample, then we can easily calculate the standard deviation of the sample. Right? Okay, now we have this t statistic. We are given the problem that we calculate the t statistic. Then the next step is obvious to check table D. Now let's look at the table D. Table D is given like this. As we said, we are going to compare to table A. We are going to have an extra parameter called degree of freedom. Degree of freedom on the leftmost. And it is the first one is 1, 2, 3, all the way up to so like 80, then 100, then 1000, and the last one is Z star. Actually, that means the degree of freedom equals infinity, or it is converted to a normal distribution. Table A, let's recall in table A, on the left column and the top left column and the top row, we are given the Z score, and in the center of the table, we are given the probabilities or the proportions. But here, because we have an extra parameter degree of freedom, we cannot have all those informations in the very simple table. So instead, you can see here, the probability is given on the top. And those are the t parameters, or like Z score. Here we call t parameters are in the middle. So this is opposite than table A. The probabilities are on the top. And also you can see the probabilities are listed with some discrete numbers. So here is 0.0005, 0.001, 0.0025, 0.005, 1%, 2%, 2.5%, 5, 10, 15, 20, 25%. So all those probabilities are limited, are discrete. So for example, we do not have a 7.5%. We don't have a 11.23%. We have only this. The reason is because of this degree of freedom here, we don't have that much space to list all of those numbers as in table A. So we need to have some compromise. And if we check table D carefully, this line actually corresponding to the Z score. Z score means look like this is table A, but for Z, for T, but with an infinite degree of freedom. And on the last column, that number is called the confidence level. So this is 99.9%, this is 99.8, and 99, 98, 96, 95, all the way to like here, 50% confidence interval. And those probabilities on the top are called upper tail probability. So this is upper tail probability. So if we recall this, if we recall this, and this is T here, for this definitely is Z score, but here is for T, then that will be probability for this one, upper tail. And recall in table A, those probabilities are for the on the left hand side. So for here, for Z score, for this Z score, these numbers are given this. So this is the difference between table A and table D. At least this from our textbook. For other reference books, usually it's which side, upper tail or lower tail, usually will be given. So we just need to be very careful to see what it is. Okay, now we discussed how to approximate the population standard deviation sigma with S, and how to calculate the t statistic with this. It's very similar to the z-score, and how to use table D, which is kind of different than table A. Next one, we are going to discuss a one sample t confidence interval. One sample t confidence interval. I believe we are already very familiar with the confidence interval for normal distribution. So here, the concepts are very similar. The level C confidence interval is an interval with the confidence C of containing the true population parameter. We have a data set from a population with both mu and sigma unknown. So both, this is the difference. We don't know mu, we don't know sigma. We use x bar to estimate mu, and we use s to estimate sigma. Then we need to use the t distribution with a degree of freedom of n-1. The practical use of t means the t star here. C is the area between the negative t star and the positive t star. So this is area. This yellow shaded area is called the confidence level C. We can find the t star in the line of table D for degree of freedom for n-1 and the confidence level C. Once we find this, the margin of error m is given by t star times s, then divided by square root of n. So here, the most important part is how to find the t star. Right? This is a little bit than how to find the z star. The t star here, we need to use the degree of freedom, and we need to use the table D, and we need to consider the n-1 and also the confidence level. As if we go back to here, so we can see from here or from there, they are the same. And for example, if we know the degree of freedom, so for any number, for example, degree of freedom equals 30, then we are looking for this line here. So degree of freedom equals 30, that means we are looking for this line. And if we know the confidence level, for example, 95%, that means we are going to look at this number. So this number here is 2.0. So this, that is 2.042. That corresponding to a confidence level 95% and the degree of freedom of 30. Alright, so here we are going to use one example to show how in detail how to calculate this kind of a problem. The example, red wine. To see if moderate red wine consumption increases the average blood level of polyphenols, a group of 9. This is n equals 9, so n equals 9. 9 randomly selected healthy men were assigned to drink half of a bottle of red wine daily for 2 weeks. Their blood polyphenol levels were assessed before and after the study. And the percentage change is presented as 0.7, 3.5, 4, 4.9, 5.9, 8.5, 7, 7, 4, 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 numbers. Those are the increases of polyphonal levels. First one, we are going to check if this is normal. So we can draw this histogram, or we have some other methods called normal quartiles. We didn't discuss it in detail in this class, but anyway, so we says the normality is not that high, it's low, but overall it can be considered reasonably normal. So this is not a topic in our class. So this here just to present this fact. It is very close to normal. So you don't need to care about this part. Okay, so now the question is, what is the 95% confidence interval for the average percent change? We are given that sample of size 9. All those numbers are the increase, the percentage increase. What we are looking for is the 95% confident interval for the average percent change. We know the confidence interval will be equals like the x bar plus minus the standard error of the mean, which will be the t star times the f and divided by the square root of n. So this is what we are looking for. This is the confidence interval. And so we need to calculate the x bar, and we need to calculate the find the z star, calculate the s, and we are given n. We know this is a t distribution. This is important. Why this is t distribution? Because we don't know the sigma. We don't know the sigma, so this must be a t distribution. In the final test, I may not tell you it's the z distribution or t distribution. So you may need to decide by yourself. You are going to use a z statistic or t statistic. The only way to determine this is if we know sigma, then population sigma, then we are going to use a z statistic. If we don't know this, we are going to use a t statistic. If we decided we are going to use a t statistic, then we need to know the degree of freedom n minus 1. For z statistic, we don't need to know, we don't need to care about this number. So here n equals 9, so the degree of freedom df equals 8, and confidence level equals 95%. Then we look at the table D here. This is only part of the table D listed here. So degree of freedom here, this equals 8. So look at this on the left hand side, degree of freedom 1, 2, 3, 4. Okay, look at this line, which equals 8. Then confidence level is on the bottom row, and this is listed here, so 95%. So this is this here. And the cross section here, this number is called the t star. So t star is equal to 2.306. Once we know t star, this one is easy to calculate. We are given those 9 numbers. We just add up all of them, then divided by 9. So we get this, and also we have a way to calculate the standard deviation. Then we know n, and we find from table D the t star. Then plug into all these numbers. We find that the margin of error equals this, and equals this times this divided by 3 equals 1.9. So the confidence interval will be Ci equals x this plus this. So this is the standard error of the standard error, and that one will be equals x bar. It said equals. Let me see if x bar is already calculated here, equals 5.5, and the s equals 2.517. In the homework or in the test, either this is given for large size of data, or you can calculate by yourself for smaller set of data. Right? So once we get this, we plus minus FEM, which is 1.9. So this gives us the minimum equals 3.6 to 7.4. So give us this reason. Give us this interval. This result only gives us a 95% confidence interval. Shows how large the increase is. We can see we are 95% confident that the percentage increase will be between 3.6 to 7.4. But we don't know if this can have an impact on the man's health. So that is not, this result, that conclusion cannot be obtained from this result. So up to this point, we finished how to calculate the confidence interval for a t distribution. The next is it's very straightforward. We need to know how to do one sample t test, significant test. If we still remember how to do the z-test, significant test for normal distribution, then there's no difficulty how to do this one sample t-test. And we start from stating the null and alternative hypothesis, H0 and HA. Then we decide on a one-sided or two-sided test. Then we choose a significant level alpha before the experiment, or this alpha is given. We calculate the t statistic and its degree of freedom. So this part is different than what we had before. For this significant test, we don't need to care about this. We only calculate the z statistic. So here we need to calculate t and its degree of freedom. Then we find the area and the curve with table D instead of table E here. Then the last we stating the p-value and interpreting the result. So here the p-value also because of the difference between table A and table D. In table A, the p-value is in the middle, is in the center. So this is the table, this is the t, these are the z scores, and the p-value is in the middle. So this is for table A. This is for table A. And for table D, and this part is the degree of freedom. And this one here is the p-value. And in the middle, those are the t statistic. So here, those are the z statistic, This is p-value. And for table D, to look like this. So we need to be careful. One sample t-test, the p-value, as before, is the probability if H0 is true of randomly drawing a sample like the one we get, or more extreme in the direction of the alternative hypothesis, or represent the probability that random fluctuations alone could have generated a result that differs from H0 in the direction of HA. By at least as much as what you observed in your data. This explanation is very lengthy, but we should understand. So this is correct. The p-value is calculated as the corresponding area and the curve. We have a one-tailed or two-tailed, one-sided or two-sided, depending on the HA. As in the z-test, if for one-sided test mu greater than some value, specific value mu0, then we are going to calculate the area for this one. So probability of t greater than that small t. For one-sided test on the left tail, then this mu is less than a particular value mu 0, then we are going to calculate the probability that capital T is less than or equal to small t. And for two-sided test, H is not equal to this. That means we need to calculate the area or the probability on both sides. So we use only one to the T greater than or equal to the T absolute value, and we multiply by 2 here. So this. Keep in mind there's 2 here. We use one example to show how to use table D to calculate this p-value. So here, this is presented of the table D. Suppose we calculate the degree of freedom equals 9. Right? We already know that. And we calculate the T statistical equals 2.70. We assume we already know these two numbers. Now, let's look how to find the p-value. First one, look at this df equals 9, which is here, equals this line. So we are only care about this line, this row. All others, we don't care. It's useless in our example. So only this row. The next one is the t equals is given, or we calculated equals 2.7. As we said, in this table D, the t is in the center. P-value is on the top. So we are looking for, because we know t equals 2.7, so we are looking for 2.7 in the center of the table. Definitely, because all those data are very discrete, so we definitely, most probably cannot find exactly the 2.70. So we are looking for only this line, and look at this. Okay, this one is 2.39, this one is 2.82. So 2.7 must be somewhere in the middle between these two numbers. Then, correspondingly on the top, that corresponding p-value will be between 1% and 2%, so it will be somewhere here. Because this one is called the upper tail probability, so that means like this. So here, this one. And if for one-sided test, this is the p-value. So you can see the p-value is not exact. It gives us a range. It's between 1% and 2%. We don't know exactly it equals 1.5 or 1.6. We can do some interpolations, but that is most probably that is not necessary. So we only need to know the range. So from t here equals between these two numbers, then the p-value must be between these two probabilities. So this is for a one-sided test. For two-sided test, then we just use these two numbers multiplied by 2 correspondingly. So for two-sided test, this one will be between 2% and 4%. So this one times 2 will be 2%. This one times 2 will be 4%. So this is the difference between one-sided test and two-sided test. Okay, last we are going to use the example to show in detail how to calculate this, how to do the t-significant test. We return back to the sweetening cola example. The question we are going to ask is there any evidence that storage results in sweetness loss for the new cola recipe at 5% level of significance? So R equals 5%. Remember that we are given the 10, right? The n, we know the n equals 10, and we are given all those 10 percentage increase changes. Because we know the step 1 is to state the hypothesis, H0 and H8. We are interested in if there are any evidence that the storage results in the sweetness loss or not. So the H0 will be mu equal to 0. That means no sweetness loss. Or alternatively, there is a loss. That means the sweetness will be reduced. We are not saying the sweetness will be changed. That means increase or decrease. Here we only see we are only increase to test if it will be decreased. So that is one-sided test. So this is step 1. Then step 2. So we write here step 1. Step 2 is we calculate the t statistic. And x bar, we are given the 10 numbers. We calculate the x bar. It is equals x bar equals 1.02. So we should not have any difficult calculate this number. And mu 0 is our H0, so mu equal to 0 here. So this one is this. Then divided by S. S is from that sample of size 10, so we should not have any difficult calculate the S. And this S is calculated as 1.196. And N is the sample size which equals 10. So that N here is this. Right? We are given all these 4 numbers, they will plug in, they will calculate T equals 2.70. So now we need to state our conclusion. So basically we have 2 methods. So we have 2 methods to get our conclusion. So the method 1 is this. For this 5% confidence level, right? For 5%, and we are looking for this. So this is method 1. Method 1 is here. For 5% significant level, and the critical value T alpha equals 1.833. If we draw this one here, this T is 1.33 here. So this one is here. And our T is 2.7 here. So our T here is 2.7 here. But this one is 1.33. So we can see our T is larger than this one. That means our probability is more significant. Our probability is smaller than this, so is smaller than 5%. So that means the result is significant. So this is the first one, first method. The second method is definitely we need to calculate the p-value. The p-value is very simple. We already discussed in the last slide here. Right? T equals 2.7, degree of freedom because n equals 10, so df equals 9. Looking at this line, and t equals 2.7 is between 2.3 and 2.8 is somewhere in between these two. Then the p-value will be between 1% and 2%. And we know we are interested in a one-sided test, so that the p-value will be larger than 1%, less than 2%. So the p-value is larger than 1%, less than 2%. As we said, we don't know the exact value of the p-value. Right? We only know it's in this range. But the good news is we know no matter what value is inside this range, it is always less than this alpha, which is 5%. So that means the result is significant. The t-test has a significant p-value, so we are going to reject H0. H0 means there's no change in the sweetness. That means there's no sweetness loss. And we cannot accept H0. So our conclusion is we reject H0. Or there is a significant loss of sweetness on average following the storage. For the calculation of the bean here, so we are given these 10 professional testers and this the numbers are given here, so the average equals 1.02. So that how we calculate this. The standard deviation is also calculated from here.